Hey ladies, so today we are starting chapter 11. This is the last chapter in our whole course. This is so exciting. You guys have made it this far. I'm sure you guys are probably jumping for joy right now, so that's super exciting. So here we're doing chapter 11. So apparently each one is so specific and so important enough that each section in this chapter was combined to make the chapter name. So we're going to be dealing with permutations, combinations, and the binomial theorem. So we're going to deal with each of these topics in different sections. So just a note here, notice that our unit here is only 6 hours long. So it's kind of along the same lines of what we've been doing before. So there's 3 sections, assignment, review, then a test. So it'll come back pretty fast, and that should all be, pretty much most of the assignments and assessment will be next week. So, but just keep your eye out for that, okay? And the outcome that we're going to be achieving 2 in this unit. They're dealing with understanding permutations and dealing with combinations, including our binomial theorem. Some key terms that we're going to be looking at are the fundamental counting principle, factorials, permutations, combinations, and the binomial theorem. So to start here, we're doing with section 11.1. So this one here, we're going to be talking about permutations. And so to start off, the fundamental counting principle. So the fundamental counting principle states that if one task can be performed in a number of ways and a second task can be performed in b number of ways, then the 2 tasks can be performed combined in a times b number of ways. Okay? So you just multiply the number of ways together, and when you take that combination, that is the number of different ways that we can perform a task. So for example, we have a restaurant meal consists of one of 2 salad options, one of 3 entrees, and one of 4 dessert options. So looking at the different, I guess if you want to call them tasks, or we have 2 different choices for our first one, and we have 3 different choices for our second task, or I guess menu option. Then there's also one of 4, so there's 4 total choices for dessert. So then we take those numbers and we multiply them together. So there's 2 times 3 times 4, which is equal to 24 possible meals. So, you know, in different combinations, so maybe you have the first type of salad with the first entree with the first dessert, or you could do the first salad with the first entree but with the second dessert. So you could do that a bunch of number of ways, and this fundamental counting principle states that it would be 2 times 3 times 4, or 24 possible meals. Okay, so let's do an example. So in how many ways can 5 black cars and 4 red cars be parked next to each other in a parking garage if a black car has to be first and a red car has to be last? So there's 2 little restrictions that we have on here. So we're going to set this up kind of, first we're going to do a total, so we have 9 cars in total, and we can talk about, there is 9 cars, and we'll talk about those restrictions. So we have 1, 2, 3, 4, 5, 6, 7, 8, and we need 1 more. Okay, so there's 9 cars in total. So what does it matter about how we organize them? So our first one here is that, our restriction here is that we have to have a black car. And if you guys remember, the first number there are 5 black cars. So you can choose from 5 different types of black cars, as long as one of those cars is black. That one has to be the first one. Then at the very end, it says that the last one has to be a red car. So this one here has to be red. And so that number there's 4 possible choices there. And then what about the middle stuff? What does that matter there? So that one, it doesn't say. But what we're going to go through is what can we do for a second car? Does it matter? So we can actually start to rule some things out. So we have 1 car already picked out to start with. Then we have another car at the end to picked out already. So that means that there's 7 in total left for any of these ones here. So to go, starting with our second car there are 7 possibilities. So then we remove 1 to get to the next one. So that means that there's 6 cars left at this point. So there's 6 different options. Then we've eliminated one of those options because it gets chosen for that 3rd spot. Then what we're left is we have 5 different options. Then we have 4 different options. 3, 2, And then finally, we have one car left over. Okay? So what we're going to do is to find the number of possible choices that we could do for this, you multiply all of these numbers together. So what we're going to have is 5 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and then the last one there is times that by 4. So you get this like monstrous number. So if you guys put that into your calculator, how many different ways can we order or park these cars? And that will give us 100,800 different kind of ways that we can park these cars. And if I can, I want to draw your attention to this pattern right here. So this is how we start with 7, and then we multiply with a number decreasing by 1 each time. This goes from 7 times 6 times 5 times 4 and so on all the way until we get up to 1. So this pattern here is what we call a factorial. And a factorial is defined as any positive integer. So that's an important restriction there. So any positive integer n is the product of all of the positive integers adding up to and including n. And what we do is we represent this using an exclamation mark. So for example here, we have 4 factorial or 4 exclamation mark. And so you start with n and then you decrease up until you get to 1. So it'd be 4 times 3 times 2 times 1. So let's look at our example above, and let's turn this into a factorial. So here we have 5 and 4. Those ones don't really fit in that pattern. So what we can do is we can rearrange this. We can rearrange it as 5 times 4 and then times 7 times 6 times 5 all the way up until we get to 1. So what we can do is we can take this number here and let's write this into a factorial. So it'd be 5 times 4 times 7 factorial. And if you guys, actually you guys can put this into your calculator. Your calculator should have a factorial button. If you guys can't find it, look it up either using YouTube, Google, or you can come see me. Typically how it's expressed on your calculator will be n exclamation mark. This is usually the button. Most times it's you usually have to push like a second function sort of thing. So keep our eye out for that. But your calculator will do this work. But it's always nice to understand how factorials work. And going on the basis of understanding factorials, this one might be a bit of a mind-blowing. It's kind of one of those exceptions to the rules, but they made this own rule for what the factorial of 0 is. And most people are like, well, it's 0, but no, it's 1. You guys can look up, there's a million different types of proofs saying that 0 factorial is 1. It's kind of, I like to more just think about it as a rule. That's how it's stated. It makes it work for factorials if we stick with this kind of principle or rule. I also like to think about it as even there's only one possibility or one possible way to choose 0, and so there's one way to choose 0, which is just 0. So I kind of think about it that way, but there's a million proofs if you guys are interested in. So I'm not going to get into specifics about that. I definitely do encourage you though to look that up. But if not, we can just think of this as a general rule that we're just going to accept, that 0 factorial is 1. Okay? So let's get into what a permutation is. So a permutation is an ordered arrangement or sequence of all or part of a set. So for example, if we were to look at the possible permutations of the letters A, B, and C, we can come up with these wonderful different arrangements. So there's ABC, ACB, BAC, BCA, CAB, and CBA. So those are all the different types of arrangements or sequences that we can create using ABC. And one little important distinction here is that with permutations, whether or not we repeat, it does matter. So what we're going to look at next section is, what happens if they don't matter. I'm not going to get into the specifics. We're going to look at that next section, okay? But so for this one, it could be any possible combination. Doesn't matter if we repeat letters or what we do. So that is essentially a permutation. So it's an ordered arrangement. So we can represent permutations using the notation we have subscript n, p subscript r. So this represents the number of permutations or arrangements in a definite order of r terms taken from a set of n definite items. And so these keywords here are definite. It's a definite order. So what we're going to be looking at combinations is that it doesn't matter what it is. Here it absolutely matters. So A, B, and C is not the same as A, C, B. Those are not the same thing. So order matters. So they treat it as two different things. Okay? And so we can use, there's an equation that we can use for permutations. So let's write out our notation. So we have subscript n, p subscript r, which is equal to n factorial, divide that by n minus r factorial, where n is an element of all positive numbers, or those natural numbers. Okay? So just to go back, so here we have n is kind of our total possibilities, and r is essentially, we could say, r items that we're taking, or I like to say it's n choose r. So now let's look at some examples actually using this. So here we need to evaluate 10p6, and if we want to think about this in our terms of our variables, 10 is n and 6 is r. So let's use our equation there. So there we have npr is equal to n factorial over n minus r factorial. Okay, so let's substitute in those numbers. We know that n is 10 and r is 6. So 10p6 is equal to, that would be 10 factorial over 10 minus 6 factorial. So we can simplify inside our brackets there. So that is equal there to 10 factorial over 10 minus 6 is 4 factorial. Now if you want to, you guys are more than welcome to use your calculators, but I want to go through a little bit more of the process about what if we didn't have a calculator. Okay, so what we're going to do is we're going to change this factorial, and we're going to change it into multiplication. So remember, you start with your n, so that'd be 10, and then you multiply by the decreasing number. So you multiply by 9, then 8, 7, 6, 5, 4, 3, 2, and you guys could write 1, but 1 times anything is a number itself, so it's really just kind of a waste of breath and energy writing that 1 there. And then we can do the same for our 4 factorial, so we have 4 times 3 times 2 times 1. So this is just, we're expanding that factorial there, okay? So now what we can do to solve this is, we're dividing, all of this is multiplication, so we can start canceling out either common factors, like terms, whatever you want to call them. So here we have 4 divided by 4, 3 divided by 3, 2 divided by 2, 1 divided by 1. So what we're left with there is 10 times 9 times 8 times 7 times 6 times 5. And if you put that big, I'm sure we're going to end up with this big number here. But what essentially we're going to be left with is, we have 151,200. So that is one way you guys could have gone about this question. If I could offer you though, what we could do is, we'll do this in the next video, but we'll just leave this as, say, this number or as the factorial, and then we'll divide it by that whole factorial. So we're not going to cancel numbers, we'll just simplify the numerator, simplify the denominator, and then divide the two numbers together. And you'll find that we get the exact same thing. It's just some different options for you guys. I don't care whichever you use, you'll get to the exact same answer. So it really doesn't matter which one you guys use, just make sure it's the one that works for you. Okay, so let's move on to example number 2 in our next video.